Section 1.4, Dimensional Analysis. Learning Objectives. By the end of this section, you will be able to 1. Find the dimensions of a mathematical expression involving physical quantities. 2. Determine whether an equation involving physical quantities is dimensionally consistent. The dimension of any physical quantity expresses its dependence on the base quantities as a product of symbols, or powers of symbols, representing the base quantities. Table 1.3 lists the base quantities and the symbols used for their dimension. For example, a measurement of length is said to have dimension L, or L to the power of 1. A measurement of mass has dimension M, or M, to the power of 1, and a measurement of time has dimension T, or T to the power of 1. Like units, dimensions obey the rules of algebra. Thus, area is the product of two lengths and so has dimension L to the power of 2 or length squared. Similarly, volume is the product of three lengths and has dimension L to the power of 3, or length cubed. Speed has dimension length over time, L over T or LT to the power of -1. Volumetric mass density has dimension M over L to the power of 3, or ml to the power of -3, or mass over length cubed. In general, the dimension of any physical quantity can be written as L to the power of A, M to the power of B, T to the power of C, I to the power of D, theta to the power of E, N to the power of F, J to the power of G, for some powers A, B, C, D, E, F, and G. We can write the dimensions of a length in this form with A equals 1 and the remaining 6 powers all set equal to 0. L to the power of 1 equals L to the power of 1, M to the power of 0, T to the power of 0, I to the power of 0, theta to the power of 0, N to the power of 0, J to the power of 0. Any quantity with a dimension that can be written so that all 7 powers are 0, that is, its dimension is L to the power of 0, M to the power of 0, T to the power of 0, I to the power of 0, theta to the power of 0, N to the power of 0, J to the power of 0, is called dimensionless, or sometimes of dimension 1, because anything raised to the 0 power is 1. Physicists often call dimensionless quantities pure numbers. Table 1.3. Base quantity. Symbol for dimension. Length. L. Mass. M. Time. T. Current. I. Thermodynamic temperature. Theta. Amount of substance. N. Luminous intensity. J. Table 1.3, Base quantities and their dimensions. Physicists often use square brackets around the symbol for a physical quantity to represent the dimensions of that quantity. For example, if r is the radius of a cylinder, and h is its height, then we write open bracket, r, closed bracket, equals, l, and, open bracket, h, closed bracket, equals, L to indicate the dimensions of the radius and height are both those of length, or L. Similarly, if we use the symbol A for the surface area of a cylinder, and V for its volume, then open bracket, A, closed bracket, equals, L to the power of 2, and, open bracket, V, closed bracket, equals, L to the power of 3. If we use the symbol M for the mass of the cylinder, and ρ for the density of the material from which the cylinder is made, then open bracket, M, closed bracket, equals, M, and, open bracket, ρ, closed bracket, equals, ml to the power of -3. The importance of the concept of dimension arises from the fact that any mathematical equation relating physical quantities must be dimensionally consistent, which means the equation must obey the following rules. 1. Every term in an expression must have the same dimensions. It does not make sense to add or subtract quantities of differing dimension. Think of the old saying, you can't add apples and oranges. In particular, the expressions on each side of the equality in an equation must have the same dimensions. 2. The arguments of any of the standard mathematical functions such as trigonometric functions, such as sine and cosine, logarithms, or exponential functions that appear in the equation must be dimensionless. These functions require pure numbers as inputs and give pure numbers as outputs. If either of these rules is violated, an equation is not dimensionally consistent and cannot possibly be a correct statement of physical law. This simple fact can be used to check for typos or algebra mistakes, to help remember the various laws of physics, and even to suggest the form that new laws of physics might take. This last use of dimensions is beyond the scope of this text, but is something you will undoubtedly learn later in your academic career. Example 1.4. Using dimensions to remember an equation. Suppose we need the formula for the area of a circle for some computation. Like many people who learned geometry too long ago to recall with any certainty, two expressions may pop into our mind when we think of circles. Pi r squared and 2 pi r. One expression is the circumference of a circle of radius r and the other is its area. But which is which? Strategy. One natural strategy is to look it up, but this could take time to find information from a reputable source. Besides, even if we think the source is reputable, we shouldn't trust everything we read. It is nice to have a way to double-check just by thinking about it. Also, we might be in a situation in which we cannot look things up, such as during a test. Thus, the strategy is to find the dimensions of both expressions by making use of the fact that dimensions follow the rules of algebra. If either expression does not have the same dimensions as area, then it cannot possibly be the correct equation for the area of a circle. Solution. We know the dimension of area is L squared. Now, the dimension of the expression pi r squared is open bracket, pi r squared, closed bracket, equals, open bracket, pi, closed bracket, dot, open bracket, r, closed bracket, squared, equals, 1, dot, L squared, equals, L squared. Since the constant pi is a pure number and the radius r is a length, therefore, pi r squared has the dimension of area. Similarly, the dimension of the expression 2 pi r is open bracket, 2 pi r, closed bracket, equals, open bracket, 2, closed bracket, dot, open bracket, pi, closed bracket, dot, open bracket, r, closed bracket, equals, 1, dot 1, dot L, equals, L. Since the constants 2 and pi are both dimensionless and the radius r is a length, we see that 2 pi r has the dimension of length, which means it cannot possibly be an area. We rule out 2 pi r because it is not dimensionally consistent with being an area. We see that pi r squared is dimensionally consistent with being an area, so if we have to choose between these two expressions, pi r squared is the one to choose. Significance. This may seem like kind of a silly example, but the ideas are very general. As long as we know the dimensions of the individual physical quantities that appear in an equation, we can check to see whether the equation is dimensionally consistent. On the other hand, knowing that true equations are dimensionally consistent, we can match expressions from our imperfect memories to the quantities for which they might be expressions. Doing this will not help us remember dimensionless factors that appear in the equations. For example, if you had accidentally conflated the two expressions from the example into 2 pi r squared, then dimensional analysis is no help. But it does help us remember the correct basic form of equations. 1.5. Check your understanding. Suppose we want the formula for the volume of a sphere. The two expressions commonly mentioned in elementary discussions of spheres are 4 pi r squared and 4 pi r cubed over 3. One is the volume of a sphere of radius r, and the other is its surface area. Which one is the volume? Example 1.5. Checking equations for dimensional consistency. Consider the physical quantities s, v, a, and t, with dimensions, open bracket, s, closed bracket, equals, l, open bracket, v, closed bracket, equals, lt to the power of -1, open bracket, a, closed bracket, equals, lt to the power of -2, and open bracket, t, closed bracket, equals, t. Determine whether each of the following equations is dimensionally consistent. A, s, equals, vt, plus, 0.5, a, t squared. b s equals v t squared plus 0.5 a t and c v equals sine a t squared over s. Strategy. By the definition of dimensional consistency, we need to check that each term in a given equation has the same dimensions as the other terms in that equation, and that the arguments of any standard mathematical functions are dimensionless. Solution. A. There are no trigonometric, logarithmic, or exponential functions to worry about in this equation, so we need only look at the dimensions of each term appearing in the equation. There are 3 terms, 1 in the left expression and 2 in the expression on the right, so we look at each in turn. Open bracket, s, closed bracket, equals, L, open bracket, v, t, closed bracket, equals, open bracket, v, closed bracket, dot, open bracket, t, closed bracket, equals, L, t to the power of -1, dot, t, equals, L, t to the power of 0, equals, L, open bracket, 0.5 a, t squared, closed bracket, equals, open bracket, a, closed bracket, dot, open bracket, t, closed bracket, all squared, equals, L, t, to the power of -2, dot, t to the power of 2, equals, L, t, to the power of 0, equals, L. All 3 terms have the same dimension, so this equation is dimensionally consistent. B. Again, there are no trigonometric, exponential, or logarithmic functions, so we only need to look at the dimensions of each of the 3 terms appearing in the equation. Open bracket, s, closed bracket, equals, L, open bracket, v, t squared, closed bracket, equals, open bracket, v, closed bracket, dot, open bracket, t, closed bracket, all squared, equals, L, t to the power of -1, dot, t squared, equals, L, t, open bracket, a, t, closed bracket, equals, open bracket, a, closed bracket, dot, open bracket, t, closed bracket, equals, L, t to the power of -2, dot, t, equals, L, t to the power of -1. None of the 3 terms has the same dimension as any other, so this is about as far from being dimensionally consistent as you can get. The technical term for an equation like this is nonsense. C. This equation has a trigonometric function in it, so first we should check that the argument of the sine function is dimensionless. Open bracket, a, t squared, over s, closed bracket, equals, open bracket, a, closed bracket, dot, open bracket, t squared, closed bracket, over open bracket, s, closed bracket, equals, L, t to the power of -2, dot, t squared, over L, equals, L, over L, equals, 1. The argument is dimensionless. So far, so good. Now we need to check the dimensions of each of the 2 terms, that is, the left expression and the right expression, in the equation. Open bracket, v, closed bracket, equals, L, t to the power of -1. Open bracket, sine, open parenthesis, a, t squared, over s, closed parenthesis, closed bracket, equals, 1. The 2 terms have different dimensions, meaning, the equation is not dimensionally consistent. This equation is another example of nonsense. Significance. If we are trusting people, these types of dimensional checks might seem unnecessary. But, rest assured, any textbook on a quantitative subject such as physics, including this one, almost certainly contains some equations with typos. Checking equations routinely by dimensional analysis saves us the embarrassment of using an incorrect equation. Also, checking the dimensions of an equation we obtain through algebraic manipulation is a great way to make sure we did not make a mistake, or to spot a mistake, if we made one. 1.6. Check your understanding. Is the equation v equals a t dimensionally consistent? One further point that needs to be mentioned is the effect of the operations of calculus on dimensions. We have seen that dimensions obey the rules of algebra, just like units, but what happens when we take the derivative of one physical quantity with respect to another, or integrate a physical quantity over another? The derivative of a function is just the slope of the line tangent to its graph, and slopes are ratios, so for physical quantities v and t, we have that the dimension of the derivative of v with respect to t is just the ratio of the dimension of v over that of t. Open bracket, dv, over dt, closed bracket, equals, open bracket, v, closed bracket, over, open bracket, t, closed bracket. Similarly, since integrals are just sums of products, the dimension of the integral of v with respect to t is simply the dimension of v times the dimension of t. Open bracket, integration of v dt, closed bracket, equals, open bracket, v, closed bracket, dot, open bracket, t, closed bracket. By the same reasoning, analogous rules hold for the units of physical quantities derived from other quantities by integration or differentiation.